All right, let's talk about percent composition by mass. So this is not a hard process to get good at. I don't think it's just a simple multiplication and division type stuff. And it allows you to go further and work with what are called empirical formulas and some other cool stuff. So that's for next time though. So let's begin by just remembering what a chemical formula is. You know, a chemical formula shows you two things, basically. It shows you what elements are in the compound, and then it shows you how many atoms of each element there are in that compound. So, like if you have something like, oh, I don't know, let's say that we have a real easy one, NaCl. Okay, so we don't have any subscripting here. It's basically we just see that there's sodium and there's chlorine in this compound, and that there's one atom of sodium, or ion I guess, and then one ion of chloride. Okay, a little more complicated formula might be something like calcium phosphate, like Ca3PO4 2, and so this one with these parentheses and an outside subscript, you know, you gotta it's easy to see what elements are there, but then you have to do a little very easy math to determine how many of each atom there are. So 3 calciums, the 2 would distribute to the phosphorus. We have so 2 phosphorus atoms, and then 8 oxygen atoms, right? So that's what a chemical formula does for you. What a chemical formula, though, lacks is the ability to show you basically the composition of the mass distribution in the formula. So even though something like sodium chloride, for example, looks like it's, you know, it's made from two things, sodium and chlorine, and you might think, well, that means it's 50% sodium and 50% chloride. Kind of the formula makes it look like that might be the case, but that is not the case. Even though it's a 1-to-1 ratio, the difference in mass between sodium and chlorine leads to a difference in percent composition within the compound. So, like if you look at this visually, sodium is this kind of relatively dinky little ion here. This is the sodium portion of the compound. Its atomic mass is only like 23 or something like that, 22.99. And then chloride ion is quite a bit bigger. So here's the chloride part of this. So sodium and chloride. And when you look at it like this, you can tell that sodium chloride is not 50% sodium and 50% chlorine. It's some other percentage, right? So don't be fooled by the subscripts in the formula. That's not really what tells you the percent composition. That just tells you the ratio in which the elements are bonded together. So let's figure out how we're going to calculate how much of this actual substance is sodium and how much is chloride. Okay, so when we do percentages, you guys do percentages all the time because you're always trying to calculate the grade you got on a test or something like that. And the way you do that is like if you, let's say you didn't do so good on a test and it comes back to you and you got like like a 12 out of 27, right? So sometimes on a test, I'll just leave that as your score, and I just basically leave you to figure out how you did. The way you would solve this is basically, you know, you take 12 and you divide it by 27, and then you multiply that answer by 100, and that is what would give you a percent. So really what you've done here is you've taken a part. This is the part that you got correct. And then this would be the total number of questions on the test, right? So you're basically dividing the part over the total. That's going to always give you a decimal. And that decimal is then multiplied by 100 to get you your final percent. Okay, so that's how you calculate a percent. And when we do percent composition in chemistry, when we look at chemical formulas, it's the same thing. Okay, so let's do a couple of practice problems here. So let's actually look at sodium chloride. So the question that you'll see is going to be something like this, like what is the percent composition by mass of Na and of Cl. Okay, so here we're going to follow this same like part over total kind of thing that we did up here with these numbers. And so what you want to do is take the total molar mass and that's going to be your denominator in this fraction. That's the total that's like this number here, okay? And then you're going to put each element's mass contribution above the total. So for sodium, we're going to have to do two problems here, one for sodium and then one for chlorine. So sodium's mass over the total molar mass times 100 is going to give you the percent composition of sodium. Okay, and so let's run through those numbers. So the mass of sodium individually is 22.99. All right, we're going to put that over the total mass of sodium chloride, which is sodium and chloride. That's 58.44. Okay, so that number goes here. Okay, and then we're going to divide those two numbers, which will give us a decimal, and then we're going to multiply it by 100. So 22.99 divided by 58.44 gives us 0.39333, so whatever. Leave that number on your calculator and just divide it by 100. Oh, excuse me, shoot, no, multiply it by 100. There we go. And that gives you 39.33%. Okay, so 39.33%. No, 39.34%. Okay, so as you can tell, that's not 50%. That's just about 40. So of course the other remaining percent for chlorine is going to get you to 100. But let's do the math anyway. So chlorine is 35.45 divided by that same total molar mass, 58.44. We're going to multiply that by 100. Now let's just see what we get here. So that is 35.45 divided by 58.44 divided, oh, how do I do that? Times 100. And that gives us 60.66%. And of course, you know, this number 39.34, 60.66, that will add up to 100%, right? That's what you're looking for. So just doing percent composition problems based on the formula is not really so hard. So that's how that works. And it can get a little bit more complicated in a problem like this. This is about as hard as these are going to get for just percent composition problems. So this one has, here's the problem. In a 347.721 gram sample of ammonium nitrate, how many grams of nitrogen are there? Okay, so what we got to do is basically figure out the percent composition, and then we're going to apply that percent to this original sample size. So we're going to do it the same way we did before. The formula for ammonium nitrate is NH4 and NO3. It's a +1 oxidation, -1 oxidation. We don't need any more subscripting, so that's the formula, okay? The molar mass of this, the total molar mass of this is 80.05 grams per mole. So that's the number that we're going to use as our denominator, okay? So if we want to know how many grams of nitrogen there are in this sample of ammonium nitrate, you know, the ammonium nitrate contains nitrogen, but it also contains hydrogen and oxygen. In this question, we're just concerned with how much nitrogen there is. And so we're going to take nitrogen's total contribution to the compound, and then we're going to divide it by the total molar mass of the compound. So keep in mind we have 2 nitrogen atoms here. So each nitrogen atom is 14.01. So that means that nitrogen's contribution to this amount is 28.02, which we're going to divide by the entire total molar mass of the compound, which is 80.05. Okay, now instead of doing this division and multiplying it by 100 like we did in the last couple problems, we're going to get this decimal, which is a decimal representation of the percent, and we're going to multiply that decimal by the original sample size number. And that's where people go wrong. They multiply this decimal by 100 and then try to multiply that percentage by the sample size, and that's not going to work. So let's figure out what the decimal is here. This is 28.02 divided by 80.05. So that decimal that we get here is 35.00. Oh, whoops, excuse me, 0.3500. All right, so that number we would have multiplied by 100 if we were just looking for the percent composition of nitrogen, but we're not. We're looking for the grams of nitrogen. So we're going to take the decimal that came out of this fraction and we're going to multiply it by the original sample size here of 347.721, and that's going to give us our final answer. So 0.3500 times 347.721, and that gives us 121.7 grams. Okay, so of that 347.721 grams of ammonium nitrate, we would be able to tease out a total of 121.7 grams of nitrogen. All right, and that's about as difficult as those problems get, and even that's not that hard. All right, good.